B really means f of q, and here we really do have a notational variation because b is a single variable, now q is a point in the plane. Okay, anyhow, if p equals x of a, y of a, then we can say that f of a means f of p. Again, a is a value of t at the initial point of this curve, and f of a then means f evaluated at the point x of a, y of a, point we call p. Now with this notation, we see that f of b really means f of q, and f of a really means f of p. The notational inconsistency is bound to be a little bit confusing. The alternative used by most authors is going to be to give this function f of xy a different name when you're referring to it as a function just of t. For example, we'd call the function g, and here we'd say dg dt equals all this, which is going to equal this. So now we're talking about dg dt integrated with respect to t, so we get g of t from a to b, g of b minus g of a. Then we relate the g function back to the f function. That is also notationally a little bit confusing, and not sure I've made the right choice here, but you can also read your text and understand that from about here to here, your text will often talk about a function with a different name, g or h or something like that. The ultimate result, however, is not that difficult to picture. We got a plane, and we got a point P, which I'll indicate by this point. Let's put a big circle around it so we can see where P is, and another point Q. P is x of a, y of a, Q is x of b, y of b, so that this should give some meaning to what we've just done. And here we have some path from P to Q. And what are we doing? We're integrating the del f, the gradient of some scalar function f from here to here. So we depict some vectors lying along this curve that are supposed to indicate our del f. We remind ourselves that what's really going on here is we're integrating over typical delta si's. We're integrating xi prime I plus y prime j delta t. Rather, our displacement, our delta, and let me fix a notation here for a minute. I've written a del operator when I should have written a delta. Okay, I've made that correction. This is a delta SI. A typical interval, we have a delta SI. We have an x of ti, y of ti, ti star at the sample point. We've evaluated del f at the sample point by evaluating x and y at the sample point, feeding those into the function. And we recall that the integral of del f dot delta si just means we're taking the component of del f in the direction of delta si, projecting it onto delta si, multiplying by delta si. Typical interpretation would be this is the work done by this del f function over the interval delta si. The contribution of this interval to the integral, the contribution to the integral corresponding to this interval is just then the dot product of these two expressions, where x prime and y prime are both evaluated at the sample point. So bringing yourself into the context of the meaning of this line integral, we see that the integral over this curve has this interpretation. It's what the integral means. The result that we've just obtained tells us that this integral doesn't depend on what path we choose. It just depends on the endpoints of the interval. It just depends on the value of the f function, not the del f function, but the f function itself at the endpoints of this interval. So we take the value of our f function at this point and subtract the value of the f function at this point, and that gives us the entire integral. And that's a really very neat result. It also has the implication that if we choose another path, okay, so we got one path here, we got another path here. If we integrate over this path, we get the same thing, that the integral of del f dot ds over the curve is equal to f of q minus f of p for any path from p to q. And let's look a little more closely at the analogy between this result, which we've just stated and more or less derived. We haven't been completely rigorous. We haven't set all the conditions on the curve and on the function, but we get the idea. Okay? Here's the fundamental theorem for a function of one variable. Again, that simply states the integral of the derivative of a function big F is the change in the value of f. Here we have a statement that the integral of the gradient of a function little f is equal to the change in the value of little f between the endpoints of the curve over which we integrate. We can thus say that since del f is analogous to the derivative, it actually generalizes the concept of the derivative. We're saying that the integral of the generalized derivative of the function little f is equal to the change in the value of little f, where we integrate the generalized derivative over a path C that runs from a point P to a point Q. So this is a change in the value of f from point P to point Q. I'll comment that nothing in anything we've done here really restricts this argument to functions of two variables. We can do a gradient of a function of any number of variables, and the expressions look identical. We just have more unit vectors, one for each dimension in each of these expressions, but we still are going to end up with something that's the differential of some function of one variable, can be integrated and obtain a very, very similar result. Now remember, we started with the conjecture that the integral of del f dot ds is 0. Let's just take a look again at this picture. And the conjecture was that del f, the integral del f dot ds is 0 over any closed curve. Okay, well, if we look at this picture, if we start at P and go to Q, we get an integral which is equal to f of Q minus f of P. Now, if we start from P and go to Q along this path, we get the same thing. If we start from P and go to Q, then from here to here, our integral is f of Q minus f of P. If we go from P around, or from Q around to P now, then our integral should be f of P minus f of Q. So that if we go from here to here, and then from here to here, we get equal and opposite results, meaning that the integral around this entire closed path is 0. Now that depends on the gradient of f being defined everywhere within a certain region, but this is so provided f behaves well enough to find a good del f within some surrounding region. And the way the proof is generally done and stated in a textbook, you'll find that the conditions for the behavior of the function f and the behavior of the function del f, and also the behavior of the curve, are nicely defined.